Okay, nice. So let's start our session. So first talk will be Professor K.Han from Shanghai University. Progress and status of neutrinoless double beta decay experiment. 20 minutes. Please.
Okay. First of all, I would like to thank the organizing committee for this chance to talk about neutrinoless double beta decay. I realize this is a huge topic. I'll go very briefly about the physics of this double beta decay and experimental research internationally, especially the few major ones, including CUORE, Cupid, Legend, Nexo, and Camlan Zen. And then probably I'll focus my last 10 minutes on the R&D effort in China to highlight the not so familiar experiments in China. So first of all, as you are all very well known, the neutrinoless double beta decay is a very active subfield in particle and nuclear physics. It probes the Majorana or Dirac nature of neutrinos. And also, it goes beyond the neutrino physics. If this happens, two neutrons decay into two protons and two electrons, but no neutrinos coming out. So this is an active, very obvious lepton number violating process. And the neutrinoless double beta decay also measures the effective Majorana mass, which relate the neutrino double beta decay to the neutrino oscillation physics via the so-called effective Majorana mass. Actually, this is defined by the sum of the first row of the PMNS matrix element squared times the 3 mass eigenstates Mi of neutrinos, and this is usually plotted on the so-called effective Majorana mass versus the lightest neutrino plot. For the inverted hierarchy and the normal hierarchy, we have two phase space span, and currently the experimental probe is at 100 millieV level here, and the next generation experiments aim to go to 10 millieV, so hopefully to cover the entire inverted mass hierarchy event. So first of all, the first impression from the neutrinoless double beta decay, or even the double beta decay with two neutrinos coming out, is it's an extremely rare event search. For example, even for the two neutrino double beta decay, a lot of the half-lives are on the order of 10 to the 19 to the 24th year. And in 2003, this publication listed the double beta decay of tellurium 128 versus a few other typical half-lives, life scale, time scales. For example, human life, human race, and solar system, and Big Bang, and they are all on the order of 1 to the 10th year or smaller, and probably the only relevant or much longer half-life scale, life scale, is proton decay. And for the tellurium 128 half-life, it's on the order of the 10 to the 24th year, which is the longest among the double beta decay. And for neutrinoless double beta decay, the half-life is even longer. And here also listed a few candidate isotopes to search for neutrinoless double beta decay. But the takeaway message is there are no magic isotopes. The decay rate is proportional to the phase space factor and the nuclear matrix element squared, and also proportional to the effective Majorana mass squared. And for the phase space factor, it's proportional to the Q to the 5th. And the larger the Q, the better. And you can see on this plot, the y-axis is the Q. And for calcium, and probably is the notable isotope with 4 MeV, over 4 MeVQ value. But unfortunately, the isotopic abundance is extremely slow. And for others, it's only in the range of 2 to 3 MeV, most of them. And then If we take into account the phase space factor and the matrix element, we can plot the expected half-life for a certain effective Brownian mass, for example, 50 millieV. And you can see here, this is for the major isotopes, it's on the order of 10 to 26 to 10 to 27 year. And most of the most searched after isotopes are germanium-76, tellurium-130, and xenon-136. So there are no obvious winners in this plot. So there's no magic isotope. So that's why many experiments search for double-bit decay in different isotopes with different techniques. The most important technique is to detect the energy of the electrons. The sum of the electrons would be a sharp peak at the Q value if it's a neutrinoless double-bit decay. If it's a true neutrino double-bit decay, the sum will be a continuous spectrum where part of the energy will be taken away by neutrinos. And this is the focus of the rest of the talk as well. So for almost all the experiments we measure the electron energy. And the half-life sensitivity from the experiment is actually proportional to the isotopic abundance, the detecting efficiency, and the square root of the detector mass times the measuring time divided by the background rate and the energy resolution. Obviously, the larger the detector, the longer the measuring time, the better. Of course, the lower the background and the narrower the energy resolution, the better. But there are always trade-offs in experiments. You cannot get the best of all the terms. And it's extremely rare event for the very small signal. For example, if we're talking about effective Brownian mass on the order of 10 millieV for a 10-ton scale experiment, we are expecting fewer than one event a year. So we have to be really careful about the background suppression and try to improve our detector performance as much as possible. And for one of the most important background is muons. That's why we always go to the underground to do the experiment. They are here on this figure. We just listed a few of the major underground labs around the world. And you can see here, for every one of them, there are at least one or more neutrinoless double-bit decay experiment listed. I'm sorry, this is not of course, this is not a complete list. I may have missed some of the experiments. And if we group them into detection techniques, you can see we can detect the electrons, measure the electron energy via photon or electrons, or a combination of two of them. For example, CUORE bolometer measures only the photon signal as the temperature rise. And for a photon signal, a typical one would be chemolysine with scintillation. And for electron ionization signal, experiments such like Goda-Majorana, Legend, CDEX all use high purity germanium detectors for this purpose. So this is a very active, very versatile field. We can also separate them, group them into a solid state detector arrays, all gas liquid detector. On the left is detector arrays with a large number of detector modules, each of them on the kilogram scale. And for the Cupid, it's LMO crystals, and for the Legend, it's high purity germanium. And on the right is gas or liquid detector. It's one large monolithic detector. For example, chemolysine is a large liquid scintillator with a mini balloon inside, and Nexo is a liquid xenon TBC. There are counterparts in China. I'll talk about this more later. And just very quickly about the few large projects. For CUORE Cupid, we search for double-bit decay of tellurium-130 with 988 tellurium crystals. It runs as a bolometer array. The bolometer just measures the temperature rise. Once there's the MeV scale energy release, we have a very measurable temperature rise, and via the temperature rise, we can measure the energy. And I believe the next talk will be from Shalom on the CUORE, so I'll go very quickly on this topic. So currently they're running at 10 millikelvin in a large customized dilution refrigerator. This is also the so-called the coldest cubometer in the universe, because for the CUORE cryostat, it maintains 10 millikelvin for a cubometer of bolometer array. And this experiment is hosted at Gran Sasso in Italy. And I guess the most noticed result was from last year, 2022, on Nature. CUORE published the 1 ton year data, obviously with no signal, but they established the best half-life limit for tellurium-130. And from this plot, it's not highlighted, but the major background is from alpha, especially the alpha from crystal and the copper frame. So the next upgrade is to get rid of the alpha as much as possible with the so-called scintillating bolometer. If it's a scintillating bolometer response, the light output is different for alpha. Here, a smear alpha source versus the beta and gamma. And this way, when they plot the light yield versus the energy, you have two very different band. Of course, the signal would be on the top, and the alpha background would be on the bottom. So this way, you can easily separate the background, alpha background. To observe or to measure the light yield, is another smaller bolometer. It's called the light detector. Currently, Cupid is working on a lot of R&D, and I believe the next talk will also cover part of the Cupid physics program. And but physics goal is to search for the double beta decay of molybdenum 100 to the 10 to the 27th year, and the effective Majorana mass is 12 to 20 millieV to fully cover the inverted mass hierarchy. On the left is their expected background model. And here is the Cupid baseline ridge. And this gray area is the inverted mass hierarchy band. So legend is a combination of Gerda and Majorana with high purity germanium detector technology. And currently they're working on the Legend 200 with 200 kilogram of crystal at Gran Sasso as well. So this is the illustration, and this is a picture. Actually, recently they just reported their resolution numbers. They achieved the 2.5 kV full self maximum resolution for most of their detectors. It's actually a very nice looking array going on, and it's rumored that they're going to release the physics result in the next week. And the discovery sensitivity for the 200 kilogram is at the 10 to 27th year, and the next phase will be called the Legend 1000, with a 1 ton of detector to the 10 to 28th years sensitivity for 10 ton year of exposure. So they're also proposing a new type of high purity germanium detector called ICPC, the inverted coaxial detector with large mass and well maintain the good energy resolution and particle ID. So the next one is called Nexo. It's a large liquid xenon TPC with 5 ton of enriched xenon in the active volume, and the TPC read out the scintillation as well as the ionization signal from the xenon. For the scintillation light detection, they have 4.5 square meter of silicon PM with customer design ASIC readout in the liquid xenon itself, so cold electronics. And the charge collection is with silicon charge rate strips, you can see here. And it's a very ambitious program with 5 ton of enriched xenon. So this is one of the largest ones. And also the physics potential is at 10 to the 28th, on the order of 10 to the 28th year as well. So the last international project is I would like to highlight is ChemLab. It's utilizing the very successful ChemLab detector with 1 kiloton of ultra pure liquid scintillator and doped it with 3% of xenon. You can see the xenon doped into liquid scintillator is not different from sparkling water, just press xenon gas into the liquid incinerator inside a mini balloon inside the Camelin detector, and they were running at Camelin 400, and currently they're running on Camelin 800 with about 800 kilogram of xenon. And the future one is called Camelin 2000. They will upgrade the Camelin detector itself to improve the energy resolution from 4% to 2% to better search for a sharp signal peak at the Q value. So this year, they published their latest result, again pushing the xenon as the best limit for effective marijuana mass. And this different lines is just a different matrix element, which I didn't cover. So the next few minutes, I'll talk about the Chinese program. So this including the CDEX, CUPID CJPL, PANEX, NUDEX, and Juno double-beta decay. I have 10 more minutes. So actually this...
You have 5 more minutes.
Okay. Okay, so it has most of the experiments in China is located at the CJPL. It's the deepest underground in China with 6,800 meter water equivalent overburden for about 0.2 muon per square meter per day. It's horizontal access, so we can actually drive in, and we have can actually have large trucks to drive into large equipment in. It's in the southwest part of the China, in Sichuan province, where there is a Yalong River made a U-turn here, and so the peak, the mountain is sandwiched in between the two water to the river, and in between there are the water tunnels and as well as traffic tunnels. So along the traffic tunnel, they built the lab. It's called so-called CJPL, and the CJPL hosts dark matter experiments, neutrino experiments, as well as astroparticle physics experiments. So recently, it's enlarged into the so-called CJPL2 with much enlarged underground lab space. It has 4 experimental halls, A, B, C, and D. Each one of them is 40 meters tall, 14 meters wide, and 130 meters long. And it's, again, each hall is divided into 2 parts. For example, B1 and B2. Some experiment, like what I'm doing, is called PANEX, is located at the B2. And for experiments, the first one is CDEX. CDEX will have a few talks at this conference, so I just skip this part. And you'll hear Li Tao talking about CDEX next. And CJPL also has a version of the scintillating bolometer. It's called CUPID CJPL, also using the LMO scintillating bolometer. Currently, they're trying to build the first demonstrator array in the next 3 to 5 years, and the collaboration is manufacturing the large high-quality LMO crystals. This is the size of the CUPID crystals, also making the crystals with enriched materials. And the collaboration is also fabricating the NTD germanium thermistor and the corresponding readout electronics. So the current effort is working on the detector assembly and detector testing in the above ground dilution refrigerators. The NUDEX is a high pressure ion TPC. So in a typical TPC, you normally drift electrons, but in this TPC, it drifts ion because this is a selenium fluoride gas. It's a highly electronegative. So any electron will be attached to an ion, and the ion gets drifted to the ends and get read out by the tau metal CMOS. And the tau metal is extremely low noise, so it can pick up the ion signal even if there is no avalanche amplification. So they expect 1% energy resolution based on this technology. And it also has a unique capability to do the tracking. For example, if the 2 electrons of MeV scale energy goes out, it travels on the order of 10 centimeter in the gas, in a high pressure gas. So you can actually read out the tracks. So for example, as illustrated here. So this is a close-up view of the tomato chip, and the active area is this part. And this is on the order of, I believe, 2 by 3 millimeter size. And they're building the prototype detector called NEWDEX 100. And this is some of the pictures of the pressure vessel. So the neutrino double bit decay is similar to ChemLab-Zen. The idea is after the neutrino mass hierarchy program, they would make a balloon or directly dope the entire liquid cylinder volume with tellurium or xenon. And if it's tellurium, they can even dope 100 tons of tellurium, which means even if it's a natural tellurium, it has about 34 tons of tellurium-130. Is probably the largest double bit decay detector by mass. And this way, because of the sheer volume of the isotope, they are very competitive in terms of the half-life and the effective environmental mass. So the red dot is half-life, the higher the better, and the blue band is the effective environmental mass, and the smaller the better. So double bit decay can compare with Nexo, Cupid, and Legend if the doping is successful. So the last one is what I'm working on, is so-called the PanX. We actually started in 2009 as a dark matter experiment. We have PanX 1, PanX 2, and now we are running on PanX photon to work on dark matter and neutrino double bit decay. So we are running since later 2020 for accumulated 195 days of commissioning data and 154 days of physics data. So we have 250 days of data. It's a very unique detector in terms of double bit decay. It's a total absorption 5D calorimeter. We measure the 3-dimensional precision energy and the timing information for any event in the range of keV to 10 MeV. And because of the one large monolithic volume, it has very nice self-shielding effect. For any gamma, external gamma going in, it gets shielded very well by the liquid xenon itself. And we also have the event topology and particle identification capability with the so-called single-site, multi-site identification. For the liquid xenon, we have a prompt simulation signal, we call it S1, and a delayed ionization signal, we call it S2. For alphas, it's usually a large S1 followed with a small S2. For beta, it's a small S1 with a large S2. And a gamma mostly release energy via multi-Compton. So it has one S1, one simulation signal with multiple ionization signal. So this way we can separate our signal, beta signals from mostly gamma background. So and most recently, we published one result about measuring the double bit decay half-life of xenon 136 with our 95 days of commissioning data. We got a result of 2.27 plus minus 0.03 plus minus 0.09 to the 10 to the 21st year. And this can be compared with the dedicated experiments such as ChemLab-Zen and EXO 200. We also are happy with this because you can see our region of interest in our fiducial volume, the double bit decay spectrum starts to dominate instead over the background. So this way we can in the future measure this curve, the shape of this curve better. And this is the first such measurement from natural xenon TBC. And in the future, we hope to expand our physics program from 4 ton to 43 ton.
Your time is over for your talk. Please proceed to the conclusion.
And if with this 4 ton, 43 ton, we have 4 ton of 136.
But it's already 25 minutes.
I'm finished. So this is my last slide. So I just stop here.
Okay. Okay, thank you for this very nice review of double beta decay. Okay, so we have time for one short question. Okay.
For the qubit experiment, how is the scintillation property? I mean, how well is the crystal scintillating about the light yield? Thank you.
The scintillation light is not so large. You can see it from this plot. You can see the light yield is in the unit of keV per MeV. That means if we have a 1 MeV signal, we only got a 0.6 keV equivalent of energy. So the scintillation is not effective. That's one of the major challenge of the light detector. You have to pick up very small light signal.
Okay, thank you. Okay, let's thank the speaker again.
Okay, thank you very much for the opportunity.
Okay, thank you. Very nice review. We don't have time for more questions. So let's proceed to next talk. And this will be Professor Fu. Latest result from the CUORE experiment. 20 minutes, please. So we cannot hear you. Can you check your mic?
Can you hear me now?
Now we can hear you. Yeah, so
Oh,
please.
sorry. Yeah. So, can you see my screen now?
Yes, we can see it.
Okay. First of all, I would like to thank Professor K.Han have already given the very excellent review about the process and status of neutron's double beta decay experiments. And now I'm giving the latest results from the CUORE experiment. I'm also glad being here to share the results with us. So here I would like to introduce a bit the double beta decay, the phenomenon. So it's just it's a phenomenon. It's allowed by the standard model, but it's the second order weak transition. It can happen within the even mass number of nuclei. In the odd mass number nuclei, it's super suppressed by the single beta decay. So we search all the the double beta decay in the even mass number nuclei. This is the list of the isotopes which has already been measured, detected in the history. And we are searching, in the CUORE experiment, we are searching the tellurium 100.
So is it?
I can actually hear you with no problem. So
I can hear you.
yeah.
Yeah, hello, can you hear me?
Yes, now it's okay. Okay, please continue.
Okay, yeah, sorry. So here I will introduce a bit about the neutrinoless double beta decay. So it's beyond the standard model process. It violates the lepton number by units of 2, and it can be a hint about the matter and antimatter asymmetry. And from the experimental point of view, we will search for a peak at the 2 neutrino double beta decay, the endpoint. So here there are two formulas. On the bottom left, it's what we can measure from the experimental observable half-life. We will get the effective neutrino, the double beta decay neutrino mass. And the bottom right formula, it gives you the sensitivity. It's very sensitive to the detector mass and the measuring time, and also very sensitive to the energy resolution and background level. And here I will introduce about the CUORE experiment. Its full name is Cryogenic Underground Observator for Rare Events. It's hosting in the laboratory in Italy named the National Laboratory of Gran Sasso. The main objective is to observe the zero new double beta decay of the tellurium 130. And the detector is hosting a cryogen-free cryostat. Normally, it's operating at the temperature around 10 millikelvin and designed for the low radioactivity and low vibration environment. The goal of the design, there are two main goals. The first one is the energy resolution, about 5 keV at the Q value. And the second one is the low background level, and should be the 10 to minus 2 counts per keV per kilo per year at the Q value. And the technique we are selecting is the cryogenic bolometric detector. Why we selected this? Because there are 4 reasons. The first one is the detector mass is easy to be scaled and it's easy to reproduce, and it has an excellent energy resolution and gives you the very low background level. But the bolometers must be operated at the extremely low temperature. Normally it's around 10 millikelvin or 20 millikelvin. And the sensor we're using is so-called neutron transmutation doped germanium thermometers, which is really sensitive to the temperature variation. And the signal, the amplitude of the pulse signal is also sensitive to the baseline. So from the pulse shape in the right bottom, you will see our pulse. So it's sensitive also to the baseline at the base temperature. This is why we always maintaining the temperature at a stable temperature around 10 millikelvin. And how to maintain the temperature? We designed totally the custom-made dry dilution refrigerator. We call that just a cryostat. And it cooled down already 1.5 ton of the material at the base temperature for 5 years. The first stage is made by 5 pulse tubes with 1 spare, and which gives you the high duty cycle without stopping. And secondly, it gives you the relative phases, the opportunity to tune the noise cancellation. And it's made by the 6 nested vessels with the decreasing temperatures. And we have 2 low temperature lead shielding. The first one is the modern one on the top of the detector to spread the gammas from the cryogenic components, and the side one is using to shield the gammas from the external sources. And in the detector space, we have 742 kilogram of the tellurium dioxide detectors, which corresponding to 206 kilogram of the tellurium 130 with a 34% nature isotope abundance. Here we have 988 crystal bolometric array, which is arranged in 19 towers with 13 floors each. Each floor it has 52 5 by 5 by 5 cubic centimeters tellurium dioxide crystals. And here I'm showing the total measurement baseline since the year 2019. So you find some fluctuations, but the huge ones we found it's really due to some earthquake or some maintenance. So in total, it's really in a stable way of the operating and measuring. And for the data acquisition, we started the data taking since 2017, and the first 2 years mainly for the cryogenic and the detector optimization, but the stable data taking since 2019 with the 90% uptime of the duty cycle. So until now, we already achieved the 2 ton year of the raw exposure data, and we published the first ton year data last year in Nature paper. And for the data analysis chain, we have several steps. Here I will just briefly introduce some main steps. Firstly, we're taking all the data in a continuum stream. So we have all the pulses without or with the signals. We will run some online triggering just for the quick data quality feedback. And we have also the offline retriggering. We call that optimum trigger. And we are using the optimum filter to fit the pulses, and we get the filtered average pulse. So in the plot in the bottom right, you will find the filtered pulses is really cut the high frequency noises. And then we have the calibration step. We are using the thorium 232 and the cobalt 60 source, and we developed the resolution fit formulas. Here you will find in the bottom right plot, we are fitting with the 3 Gaussian peak, and we considered also all the possible the contributions. So we have the multi-compton and etc. And we achieved the energy resolution at the calibration peak 2615 keV with 7.78 keV. And we can rescale or extrapolate to the Q value. We will get the 7.8 keV at the Q value. And then we also analyzed some coincidences. So from the Monte Carlo simulation, we already proved that about 88% of the neutrinoless double-beta decay events should involve only one crystal. So we are using the multi-sites to veto it, to veto it. So this is why it's important to develop the coincidence analysis. And then we run the pulse shape discrimination, which we are using the technique called the principal component analysis, where the leading component is just the average pulse. From the plot in the bottom right, you will find we developed a profile of the PCA, and once it's in the train of the red line, the shape is really compatible with the pulse shape. Once it's really far away from the red line, the pulse shape is which corresponding to the non-physics events. And with all the analysis steps, we achieved the one-to-one exposure data. So here I'm showing the full energy spectrum, and we are interested in the Q value, which is around the cobalt 6 sum line peak, has the energy 2.5 MeV. And here the different colors show the different cuts. So the gray one, it's just using the base cuts. They are just the necessary cuts gives you it's a signal, not just the noise. And the green one is plus the acid. We call that anti-coincidence. This is the one I just introduced before. So we're searching for the single sites signals, and the light green one is plus the PSD, the pulse shape discrimination, which selected the good pulse signals for the physical events, not the non-physical events. And we fit with the without signal and with the Gaussian signal fit. We set the Bayesian limit at the 90% credibility interval of the half-life. Here we show is the blue peak here. So it's the best limit we have already set. And this is all the figures of the detector performance. So we have each dataset around 1 month. In total, we have 15 datasets. And in average, all the datasets, we have 134 detectors alive. And in total, we have the exposure of the tellurium dioxide, 1,038 kilogram year, and corresponding to the tellurium 130 with 288.8 kilogram year. And the energy resolution at the Q value, we have 7.8 keV, and the total analysis efficiency here gives you the 92.4%, which is above 90%, which means our analysis also is really efficient. And from all the results we already achieved, we already did the Bayesian limits and the frequentist limits, which haven't give you any evidence of the neutrinoless double beta decay, but we set the half-life limit with the newest results. So here, from the Bayesian point of view, we had the results over 2.2 times 10 to 25 year at the 90% credibility interval, which corresponding to the effective mass smaller than 90 to 300 MeV, which we can show in the bottom right, the plot. So the yellow range is the limit we have already set, and the blue one is the sensitivity which we can achieve in the future. And besides from the results I have already shown here, we have some other results already done. So we already established the full background model results. It's not only at the region of interest, but the full end spectrum. And we run the simulations. We included 62 sources, their bulk surface contaminations, and some muons. We also consider the coincidences, and we set all the uniform pairs to get these results. And from these results, we achieved also another measurement. It's the 2-neutrino double beta decay of the tellurium-130, which is the most precise measurement of the tellurium-130 2-neutrino double beta decay half-life till today. And its value is 7.71 times 10 to 20 years. And also we have some other rare events searching. So first we have the tellurium-130 double beta decay to the first 0 plus excited state. Then we have the tellurium-128 zero new double beta decay searching, and the beta plus and the electron capture searching. So till now, these are the results which we have already achieved. And what we are doing the next, firstly, we will reach the 3-ton-year exposure, and it will running until the start of the qubit start. So the BDF was already being achieved and updated with the new analysis, such as the updated background model and the 2-neutrino double beta decay analysis. Also, the ongoing delayed coincidences analysis for the precise characterization of crystal contamination also is ongoing. And some multi-signature of neutrinoless double beta decay and 2 new double beta decay also is ongoing. Some other rare searching on the tellurium-120 is also ongoing, where some low energy analysis, which can be some help about the dark matter axions and supernova neutrinos. Besides the software analysis, we have also some hardware updating. So first, since we are sensitive to the noise, we also studied the noise and used some devices to cancel the background noise to achieve the higher baseline stability. So here I give the conclusions. CUORE demonstrates the feasibility of a tone scale experiment employing the cryogenic bolometers, and for the searching of digital double beta decay and for some other rare events. And the raw exposure already more than 2-ton a year, and achieved the new limit, and we are about to publish the new result on the top conference this year. So if you're interested, you can follow this link. And I think it's the next month, we will set the new limit of the tellurium-130. And CUORE also already released the 1-ton-year data on Nature paper, and we set the new limit without finding the evidence of neutrinoless double beta decay. And also we obtained the most precise half-life measurement of the 2 new double beta decay. And in the future, we will continue the data taking till the 3-ton-year of the exposure. And same for the unique feature of allowing deployment of different isotopes, we will upgrade the CUORE to the qubit experiment. And then this is my the presentation. Thank you for your all attention. Thank you for all questions and comments.
Thank you a lot for this very nice talk. Questions? Is there any question in? Okay, I have one question. So I have a question about your energy scale. So your energy scale is based on gamma calibration. So how this corresponds to electron energy scale? Because electrons, they will lose some energy to Cherenkov radiation. So how we count for that?
You mean the resolution here?
Not resolution, but energy scale itself. So your calibration line, they are gamma lines, and you are looking for electrons. And the electrons, they will lose some energy to Cherenkov radiation. And
Yeah, that's correct.
this will just escape. So how the electron energy scales and gamma energy scales, how they match each other?
Yeah, I'm sorry I can't answer this question. I think it's also the problem because in the beginning we have the internal source and we have some trouble in the future. So we had only the external source and which can't give you any electron calibration source, which can't give you any help of this problem. I think we do have this trouble now.
Okay, so in principle, you don't know exactly your energy scale. How you then look for the peak in the exact place?
Yeah, we predict that should be a peak at this energy range. So
you know that at 1 MeV electron, they lost about, I think, about several percent to Cherenkov radiation, if I am correct. So I think you have to check this point.
okay, yeah. Thank you for this comment. I will check it later.
More questions? Okay, no more questions. Let's thanks the speaker again for a very nice talk. Okay, our next
Thank you.
is Professor Yang, recent status and prospect of CDEX.
Hello, everyone. I'm L.Yang from Tsinghua University. Firstly, I would like to thank the organizer for invitation. Today, I will talk about the recent status and prospects of CDEX experiment at the China Jinping Underground Laboratory. Firstly, I will give a brief introduction about the direct detection of dark matter and CDEX experiments. Then I will introduce the recent status of CDEX 1 and CDEX 10 experiments. Then is the future prospect of CDEX experiment at CGPO 2, and the key technologies R&D. Lastly, I will summarize my talk. As we know, dark matter accounts for about 27% in our universe. However, we don't know what dark matter is. There are three approaches to do dark matter searches, including the direct detection in the underground laboratory, and the indirect detections with satellite outside the Earth, and the accelerator to make dark matter. For the direct detection of dark matter, we can measure the recoil spectrum between the dark matter during the dark matter scattering with our target nucleus. We can also measure the modulation of the count rates due to different modulation period. It can be divided into annual modulation and diurnal modulation. The third one is the direct detection, which nears very good angular resolution for the detector. All of them need lower background, low energy threshold, and long time stability. So here is the current status of direct detection of dark matter, and the horizontal axis is the dark matter mass, and the vertical axis is the dark matter nuclei cross section. And currently, the upper upper right corner has been excluded by current experiments. And for the high mass dark matter, the technology mainly on the liquid xenon or liquid argon detectors. For the low mass dark matter, the technology is mainly on silicon CCD, low temperature colorimeter, and germanium detectors. So we use germanium detectors to search for light dark matter. So China dark matter experiment, CDEX, is formed in 2009. Now it is about 11 institutions and about 100 people now. We use one key technology is a p-type point contact germanium detector, which is a kind of semiconductor detector and had very excellent energy resolution and lower threshold. The physics target of CDEX included direct detection of light dark matter and the germanium 76 neutrinoless double beta decay. So this is the roadmap of CDEX experiments. CDEX 1, CDEX 10, CDEX 50, CDEX 300 new, different target mass for different phases. We have now we have finished the CDEX 1 experiment and at the end of near the end of CDEX 10, and now we are building the CDEX 50 experiment, and which is have a 50 kilogram germanium detector array for diameter searches. Another one is 300 enriched germanium detector array for neutrinoless double beta decay, which you can find more information in today afternoon's Professor Wang's talk. CDEX experiment is carried out in the CGPL China Jinping Underground Laboratory, which is the world's deepest underground laboratory. It is located in Sichuan province, southwest of China. The hydrogen power station company built two dam and two traffic tunnels across the Jinping Mountain, and each tunnel is about 70.5 kilometers, and the CGPL is at the center. At the center of the traffic tunnel, and the rock overburden is 2,400 meters. Here is the muon flux is very low, measured to be 60 per square meter per year, and here is the CGPO1 picture. And the total space is about 4,000 cubic meters. And the two dark matter experiments, CDEX use germanium detector, and the PANDEX use liquid xenon TPC carry out the dark matter detection. And another is the low background facility used for the material selection for dark matter or neutrinoless double beta decay, runs several germanium detectors. First, this is CDEX 1. CDEX 1 includes two single element 1 kilogram PPC germanium detectors, CDEX 1A and CDEX 1B. It uses traditional code figure cooling system, and we have built the passive shielding with low background lead and high purity copper and polyethylene, and we use a solid indium anti-company detector used to V2. And CDEX 1 experiment is located in the polyethylene room at the CGPO1. And in CDEX 1 phases, we have over than 4 years run and over than 1,200 kilo days exposure. And the analysis threshold showed achieved about 160 EV. And this improved and extended the dark matter sensitivity to 2 GeV. Based on the CDEX 1 element, PPC element, we have built the CDEX 10 germanium detector array, which includes 3 strings with each 3 detectors. The total mass is about 10 kilogram. The detector 3 detectors is sealed into the vacuum chamber and then be immersed into the liquid nitrogen. And this phase is very important. We want to test the stability and the performance for the germanium detector immersed into the liquid nitrogen, which is very helpful for our next 100 or ton scale experiments. And the first results from CDEX 10, we use about 100 kilogram day exposure, and an analysis threshold is 160 EV, and the background level at 2 to 4 keV is 2 count per kilogram keV per day. And we have achieved the most string limit at the 4 to 5 GeV. And let's return to this formula. This formula describes the expected counter rate and different parameters. These parameters can be divided into 2 classes. One is related to the dark matter sources. One is corresponding to the physics interaction process. In our physics analysis, we consider different dark matter sources and adopt a different interaction process. So the physics content is very rich. First, we use over than 4 years data and apply the annual modulation analysis. So the annual modulation analysis provides smoking gun signatures for WIMPs independent of background modeling, while only requires background is stable with time. So this is CDEX 1B results. This results exclude the cogent signal region. Also, the DAMA phase 1, the interpretation with the spin-independent interaction under the standard Halo model in germanium crystal. This result also corresponds to the best sensitivity below 6 GeV. And for sub-GeV WIMP searches, we adopt the Migdal effect analysis. This analysis allowed us to search sub-GeV, extend the dark matter mass range to from 2 GeV to 50 MeV. So this result give us the best sensitivity in mass range of 50 to 180 MeV. We also do some searches on cosmic ray boosted dark matter. The low mass range of dark matter has been extended from GeV to keV, and the CDEX 10 results are the most sensitive than cosmology result. At the same time, we want to calculate the Earth shielding effect for low mass dark matter. So we developed a simulation package we call CGPL-ESS. We have included the detailed topography of Jinping Mountain to calculate the Earth shielding effect. So this allows us to present our result with exclusion region, not the traditional exclude line. For the dark matter scattering with electron, we have calculated the electron momentum in germanium crystal and presented the first germanium detector-based dark matter electron scattering limits from CDEX, and this gives the most stringent dark matter and electron cross-section limit to date among the experiments using solid-state detectors for mass larger than 100 MeV. In addition to traditional WIMP dark matter, we also searched for other candidates, such as the X-ions or dark photons. So we use the data from CDEX-10 experiments to search for solar dark photon and dark photon dark matter. We achieve the leading sensitivity for solar dark photon in 10 to 300 EV. And currently we are building the next stage experiment, CDEX 50. So in CDEX 50, we have a larger germanium detector array directly immersed into the liquid nitrogen for cooling and shielding. The CDEX 15 is composed of 5 strings detector array. Each string includes 10 detectors. And the background level should be is expected to be controlled 2000 lower than CDEX 10 is 0.01 counts per keV per kilogram per day at the region of interest of dark matter search is 1 keV. And the energy threshold for the data analysis is expected to be 100 EV. And the exposure will reach 50 kilogram year, and the correspond WIMP spin dependent sensitivity will reach 10 to minus 44 square cubic meters. And we beyond the traditional WIMP, we will do multi-physics channels analysis, including the X-ions, dark photons, and so on. To achieve this targets, we have many key technologies many key technologies must be well mastered, such as the large shielding and cooling system, and the germanium crystal growth, germanium detector fabrication, and the low background, low noise electronics, and the underground e-forming copper, and the cosmogenic background control, and the radon background in liquid nitrogen. So to reduce the background contribution from the vacuum chamber, we remove the vacuum chamber. We developed the bare germanium detector immersed into the liquid nitrogen directly. So here, 2 pictures show the bare germanium detector testing, and we use the ASIC preamplifier made by ourselves. You can see the detector can work very well in the liquid nitrogen, and the leakage current is stable. And to reduce the low background, to reduce the background contribution from the preamplifier and the cable, so we developed the ASIC preamplifier, use different substrate and different cable. So now the ASIC preamplifier can well work in liquid nitrogen temperature, and the electron noise can be controlled lower than 26 electron. And the detailed information you can find in this paper. to reduce the cosmogenic radioactivity in the copper. Thank you. We developed the underground eForming copper. So here the picture shows the we have built underground eForming copper prototype in CGPO1, and we developed the urine and the solid analysis by SINP MSU. For next stages, CDEX 50 or CDEX 300, we will move from CGPO1 to CGPO2, which has a larger volume to be 300,000 cubic meters. It includes 8 main halls, and we also prepared an additional pit for next generation CDEX experiment at the C1 hall of CGPL2. In this additional pit, we have built a larger liquid nitrogen tank. The liquid nitrogen volume is about 1,700 cubic meters liquid nitrogen. The size is about 30 meters in diameter and 30 meters in height. So for the germanium detector array is at the center of the liquid nitrogen tank. So for the germanium detector array, there's in every direction there's at least 6.5 meters of liquid nitrogen for shielding and cooling. So the background control target at the center is lower than 10 to minus 4 CPKKD at 1 keV and 10 to minus 6 CPKKD at 2 MeV for neutrinoless double beta decay searches energy region. Now the construction of liquid nitrogen tank has completed at 2019, and a new steel working platform has been constructed in last year, and the liquid nitrogen filling is expected to start at the end of this year. And the CDEX 50 stage is under technical design. I think the report will come soon. So let's summarize my talk. So CDEX use unique advantages of germanium detectors for low dark matter searches at China Jinping Underground Laboratory. And recently, CDEX has made great progress and published many leading results for low mass dark matter with multi-physics channels analysis and different dark matter candidates. Now we are build the CDEX 50 experiment, and the CDEX 50 will be located in the hall of C1 hall of CGPO2, and many key technologies R&D are ongoing and have made very good progress. And thank you for your attention. Welcome to visit our website for more information. Thank you.
Okay, thank you. This very nice presentation. Questions?
Thank you for a very nice presentation. I have a question about how easy to change the registration of dark matter with CDEX to registration of double beta decay for you.
Sorry, you mean why we can use one detector array to carry out the dark matter and the neutrinoless double beta decay at the same time?
Correct. You have enriched germanium 76, correct?
Yeah.
Just to remove germanium 70,
Yeah.
which is more dangerous light isotope. And you have a chance to look simultaneously to something around 2 MeV.
Yeah.
How easy for your electronics to do this job?
Okay. The first stage of CDEX 1 and CDEX 10, we mainly focus on the dark matter surface. The region of interest is about 1 keV, below 1 keV, very low energy region. This requires the low noise electronics. So we developed the low noise, low background, low mass ASIC preamplifier by ourselves. And for the neutrinoless double beta decay, we care about the energy region about 2 MeV. It's very good for germanium detector because we can use different electronics to set to different region. It can output many channels signal at the same time.
So do you mean you will have two preamplifiers in the same time?
Yeah.
So one is for low energy is what is reset preamplifier, right?
Yes.
And then the second one is you developed by your own amplifier for high energy.
No.
Or for all energy.
All by ourselves. The ASIC amplifier can output different energy region channel.
Mm-hmm. It's also reset preamplifier, or is it normal preamplifier?
Normal.
Normal preamplifier.
Yeah.
Okay.
But for low mass, low background.
Mm-hmm. Okay. More questions? There is question. I have question. So you said you will move to 100 electron volts threshold. How you will do that?
Okay, it's very difficult. I must say, but yes. Now our electronics is controlled to be lower than 200 eV, and this is our contribution from our electronics group. Yeah, now they are do more further lower the threshold. We hope we can control the 100 EV.
Okay, then I have another question. So now you said you have your threshold in 160 electron volts.
Yeah.
What is efficiency at the threshold?
Yeah, the efficiency is the trigger efficiency. The trigger efficiency is about 80%, and the
Threshold.
at the threshold 160 EV.
Yeah.
The mainly efficiency comes from the physics event and the noise event discrimination.
Okay, then I have a question. Why you don't see M line in germanium? So there is you see K line. This if you look in your spectrum, you see this one. So you see K line and 10.3 kV.
Yeah.
And then 1.3 kV L shell line, and then where is M shell?
The M. Okay. When we understand our spectrum, we can find many K shell X-rays, and the energy resolution curve at this energy region is well understand. So we can fit the L shell region at about 1 keV for different contribution from germanium, gadolinium, and other isotopes. For the K shell and L shell contribution has a ratio. This is well measurement from nuclear.
Yeah, but
physics.
my question about M. So at 170 and 160, yes. And you see nothing.
Yes, the M shell contribution is by feet, and by K shell contribution times the Km ratio.
Yeah, I think M supposed to be about 3% from K.
The M shell contribution is very low.
So this why this what was my question about the efficiency, because it seems that maybe efficiency at threshold is low.
Yeah, it's very important to well understand this. So the M shell contribution is about 10% than L ratio, L contribution. Yeah, it's very lower.
Okay, thank you. So more questions? Okay, if no question, let's thank the speaker again. And we are moving to the last talk in our session. Professor Dubinin from Moscow State University. If he's here, please.
Here is the outline of my talk. First, let me say a few words about CSO type 1 model, and then we'll discuss what to do with multi-parametric space. Here you can see the Lagrangian, which is at least 40 years old, standard model Lagrangian. Here is a Dirac term of heavy neutral leptons, which are singlets with respect to standard model group. This is Majorana term with the standard notation, left lepton doublet, Higgs. This is Yukawa mixing matrix. Then after symmetry breaking, it can be rewritten in this also well-known form, where Majorana degrees of freedom are convoluted with this object, which is 6 by 6 mass matrix, 3 by 3 Dirac blocks and 3 by 3 Majorana block. In the case when Majorana block is 0, this is called Dirac limit in the literature. Then we have effectively only Dirac fermions. But in the following, I'm going to speak about the model which includes 6 Majorana fermions. So active standard or active fermions are also Majorana. Then some long digression about the existing literature. To reconcile very small neutrino masses, we should use a very large scale of heavy neutral leptons, this capital M. And at the same time, simply to be within the reach of LHC and next collider, so to get physically interesting scenario. And at the same time, not too small mixing, which is also inversely proportional to square root from M. Somehow it should be enhanced. This is performed in 2 ways in the existing literature. Either fine-tuning of mixing matrices, which is not our case. Then additional symmetries should be applied, or using so-called Casas-Ibarra diagonalization, about which I am going to speak in the following. In the first case, when we tune on mixing matrices, then heavy neutral leptons are quasi-Dirac, and so calculations are done in the Dirac limit. In the case of Majorana fermions, this case is fully compatible with Casas-Ibarra diagonalization. So in the following, it is interesting. This is the background. It is interesting to consider some explicit forms beyond the Dirac limit, which is relatively new issue. Then returning to the Lagrangian, in order, from flavor states to mass states. Можно там вот эту погасить? Not to solve 6 or third power equations, a rather specific method of diagonalization is used when this exponent of anti-Hermitian matrix is decomposed up to second order terms. Then we have this relation between flavor states nu left and nu r, and mass states nu and n capital. So this is a well-known trick from the literature. The only thing, then a well-defined renormalizable model appears. Interactions of H and L with Z and W are shown here. The analog of Pontecorvo, Maki, Nakagawa, Sakata mixing matrix is this sort of matrix. The only important thing, of course, if we decompose not to second order, but this guy, not to second order terms, but to cubic, then additional condition appears. A specific feature of this sort of model is ambiguity, because seesaw equation and mixing matrix is defined including arbitrary matrix omega, which can be chosen unity, real valued parameter, complex valued parameter, and so on. The condition for cubic terms is shown on this slide, this one. So arbitrary matrix omega has deviation from orthogonality, which is shown by this term. Then in the following, we also favor so-called neutrino minimal standard model, which was proposed many years ago in this publication, which is simple, has no distinctive mass scales. N1, first generation HNL, is the dark matter particle, and baryonic asymmetry is successfully generated when 2 and 3 are quasi-degenerate. So what to do? It contains 18 free parameters, masses and mixings, and additional omega free parameters. So in total, 20 free parameters. What to do with this multi-parametric space? So first, what we can do to use cosmological restrictions from the side of lifetime and energy fraction of dark matter, N1. Introducing convenient variable of this sort, which omega independent contours. One can express lifetime of first generation fermion. You see, this is not the fastest decay, because decay to 3 neutrinos is possible, but this one loop decay has distinctive gamma signal, which can be detected in astrogamma observations. So it imposes the strongest restriction. Second, using this convenient variable MD, we can express the energy fraction of dark matter in the universe. It is assumed that main heavy neutral lepton production source is so-called Dodelsson-Withrow mechanism, beyond the statistical equilibrium, only production only by oscillations. So summary plot is here. This is Tremaine gun bound in blue, lifetime bound, dark matter energy fraction bound, and gray areas are from various experiments of NASA, European Space Agency. These are satellite radiometers. So a loved region is this white area, and we can see that dark matter particle mass in the region experimentally available is from 0.5 to 40 kilovolt. So, and in the following, what does this mean for parameterizations of omega matrix, this white region? I have no time here to speak in detail, so we can choose trivial omega, real valued or complex valued omega, and for angles, for Euler angles in the orthogonal matrix. For example, this figure, allowed regions are below the blue plane lifetime restriction. This is normal hierarchy. Then the right plot is inverse hierarchy, this one. And as a result, the same story for angles, deviations of angles from the favored values for inverse and normal hierarchies. So two scenarios can be distinguished. Minimal mixing scenario with the mixing of this sort, and exponential mixing scenario, very popular in the literature. If omega is taken complex valued, this additional parameter, then, for example, imaginary part of omega is of the order of 5,7. Then we have x omega of the order of 1,000. So with a very essential increase of the mixing. Now, let me turn from cosmological restrictions to accelerator ones. Here are two variables that are used by accelerator collaborations, mainly beam dump. So U alpha, which is this sum. There are, I think, 9 of them, which investigate pi and k meson decays, displaced vertices, or missing energy reconstruction. And there is also restriction from above, from Big Bang nucleosynthesis, when there is no overproduction of life, of the light elements. So let's try to use these 2 points at a full scale. In this connection, very long lyrical digression about calculations with Majorana fermions beyond the Dirac limit. Here, for displaced vertices experiment, we have to calculate lifetime very precisely. This is critical point. It is surprising that despite this technique, which was developed many years ago, calculations for Majorana fermions for this sort of Lagrangian, it follows that in our case, the Lagrangian can be rewritten in this special form only for Majorana fermions. And so we have modified Feynman rules. For example, you see here we have for 3 generations of HNL very special factor. And for example, active neutrino with Z here appears not left projector like in the standard model, but only axial vector part, because for Majorana fermion, vector current is identically equal to 0. So Majorana fermion rules are critically different from Dirac. Feynman rules. This is one more example. For Dirac fermions, these two processes, when H and L decays into lepton, antilepton, and neutrino. So in the standard model, there it would be neutrino and antineutrino. So we have two channels for one decay. For Majorana fermions, we have identical neutrino here, and this interference term appears with minus sign. And as I told you, theta with imaginary omega parameter is of order 1000. So this can be huge, despite of the fact that very small factor appears in front of it. And so one can also, if we have exchange of Z boson here, then diagram number 3 appears and interference terms and so on. It turns out that for Majorana calculations, the sign of interference terms is different for Dirac and Majorana fermions, that's C1 and C2 here, and so on. This is important point. One should mention that calculations with Dirac fermions are not always precise, and one should be very careful about them. Let me skip these unessential plots about allowed region in the imaginary omega m plane. So it is this area above the green line and below the red line, and show the result, a combination of cosmological and accelerator experimental data. In this blue area, simply displaced vertices are not observed. Lifetime is too small, and missing energy is not detected. So it is excluded by 9 collaborations. These green lines are normal and inverse hierarchy lines from BBN nucleosynthesis with Majorana technique calculations. Also, it is seen that 2 generation HNLs and 3 generation HNL give rather different bounds, which are different maybe in some cases by 2 orders of magnitude. This is the picture for electron channels. For muon channels, it is slightly worse because of uncomparable efficiency of muonic reconstruction in some cases. But one can see here also allowed and excluded regions of the parameter space. For example, here we have very small region for normal hierarchy, which is allowed. And going to higher masses of multi-GeV and collider region of 10-100 GeV, there the situation is much worse, and practically we have no restriction. And finally, a few words about lepton universality. Lepton universality parameter is defined by this formula. So the ratio of electron to muon decays, extended lepton sector to standard model, -1. And in pi and k decays, there are 2 variants of lepton universality violation. When we have real decay allowed by phase space and violation due to non-unitarity of the 6x6 mixing matrix. So, for example, in K meson decays, this plot shows that when we are around 500 MeV, then for exponential scenario of mixing, in principle, we did not simulate this precisely, but in principle, we can have some enhancement in consider with particle data group line, this bound on the level of 10 to -3. Here, 1 standard deviation is compared with 10 to -3. So Of course, this is not a strict result, but some indication where to look for. It is related to this area, approximately somewhere here. So, okay. This is the plot for lepton universality violation by means of 6x6 unitarity violation for K and pi mesons, where one can see that in comparison with experimental bounds, we have only the effect of the order 10 to minus 7, 10 to minus 8, which is too small. Yeah, so I think I will not reproduce this list of allowed mass ranges and allowed mixings. There are quite many possible regions compatible with cosmological and accelerator experimental data. But main point, in the models of CSO1 type with extended lepton sector, at least in the region of mixings experimentally accessible, we have first generation HNL dark matter mass in the region from 0.4 to 40 kilovolts. And in this region, favored point is somewhere a few kilovolt, when HNL signals at the colliders can be amplified by factors of the order of 1000 squared, so 1 million. All interference terms, which are suppressed by the ratio of active neutrino mass to heavy neutral lepton mass, are then enhanced by these factors of the order of 10 to the 6. Then the list of allowed regions, I will not, this is very simple, I will not repeat that. For lepton universality violation, some small window was found possible for discovery, potentially interesting for discovery in count decays, in which the experimental value of 4 plus minus 4, 1 sigma deviation, can be in principle exceeded. So this point is especially interesting for low energy and high precision machines like small Novosibirsk E plus E minus colliders, like VLEP 2000, for example. And finally, for minimal mixing, the BBN bound gives a strict restriction on the level of 1 to GeV. And for these masses, lepton universality violation is determined in count decays only by deviation from unitarity and is on the observable level of the order of 10 to minus 11. I have not said anything about collider signals. Collider studies are not using any explicit mixing scenarios. They are using mainly so-called model independent approach, or in other words, phenomenological type 1 CSO model. So in this model, we have only one generation of heavy neutral leptons, and mixing and mass, it is assumed that they are independent variables. So HNL masses are of the order of 100 GeV. So this is completely other story. but interesting phenomenology exists also there, which will be described by today's talk of Alexei Trutskoy. Thank you very much.
Thank you for this presentation. Any questions?
Okay, thank you very much for your interesting talk, which I'm listening for the first time. But since this is the experimental session and we are the teachers, maybe we'll try to understand each other better. In fact, I realized that personally, you mentioned here that in the process of your talk, that it is possible to use UTF and charm data in the reanalysis for getting some. This is quite understandable because you are considering the processes where neutrinos are flying from the initial state. But then you are considering the possibility of considering Y plus Y minus, some experiments on the Y plus Y minus colliders, say the ones of the Delphi collaboration, and probably the ones, and also you mentioned the results, and probably the results of our Chinese colleagues. How these your studies may be related to these studies, which project to be done with the beautiful machinery and detectors which we listened about in the previous talk.
Well, you see, thank you for this complicated question. First point here, this blue area is only a combination of that 9 collaborations which are using completely different methodics. And I would say that this is an overlap of their contours done not by us. We took that overlap from an experimental paper by Ukrainian group. It is here. This one. Physical review, yeah. So it is
present Ukrainian.
Yeah, it is not.
What is that? Two guys previously I saw them in Institute for Nuclear Research.
Yeah. So it is difficult to tell how that blue area was generated. It is a result of some extensive analysis. I can only say that such contours are model dependent. For example, the strongest restriction is from Na62 and piano collaboration here, this area. But it is calculated in the Dirac limit. So all interferences for 3-particle heavy neutral lepton decays are neglected. Here, the mass in the denominator is not too large. So for me, this is what is usually mentioned as theoretical uncertainty. And the degree of theoretical uncertainty for this blue area, from my point of view, it should be reconsidered because it is model dependent. Only Majorana or only Dirac or Dirac and Majorana, and it is very difficult at this stage to bring it to the common denominator.
I see.
Yeah, thank you. Yeah.
Okay, let us speak between ourselves.